So now we will confine ourselves to Hilbert spaces. Remember, Hilbert spaces are vector spaces which have an inner product, and in turn that inner product defines a norm. This we have done in the last class. Now we are going to basically confine ourselves to L2, the L2 space, which is also the H0 space. Look at the notes of the previous week. And we will write a linear transformation, which is basically a differential equation. Uh, Let us take a linear transformation of this sort where A is a operator, differential operator, and F is a function in H0, that is, which is same as L2 in 0 to L, let's say, or in some domain, D. Okay, now we will drop this knot and we will denote by H as H naught, okay, which also is the same as L2. So F belongs to L2, and I have a linear transformation that takes a vector in the vector space and maps it to another vector F. So now there are several examples that we can give. For example, A can be this operator, in which case you will need to have, for non-trivial solutions of this, you will need to have you'll need to have u to have two derivatives, at least two derivatives of u has to be continuous if f is a continuous function. A can be this, in which case you need four derivatives of u to be continuous if f has to be continuous. So you will have to choose u from either C2 or C4 if the domain over which this is defined is called omega, and that stretches from 0 to L. If omega stretches from 0 to L, then if A is this operator, you must have at least up to second continuous derivatives in 0 to L. If this is the operator, then it must have fourth. So in general, three definitions. First is the definition of a self-adjoint or symmetric operator in a region D, where we are using H0 as equivalent to H, which is equivalent to L2. So if AU comma V, the inner product between AU and V, is same as the inner product between U and AV, then the operator A is called self-adjoint. Remember, the inner product defined here is UV dV in D, which is the inner product between, this is the H0 inner product between U and V. So if reversing this order doesn't matter to the inner product, then you have a self-adjoint operator. Similarly, if this is self-adjoint, A is self-adjoint, and if AU comma U is always greater than 0 unless when U itself is equal to 0, apart from that it is always greater than 0, then A is called a strictly positive operator. So we will deal with strictly positive operators only and prove a couple of results for a strictly positive operator. Finally, we have learnt about the bilinear form BUV, and from the bilinear form we can generate a quadratic form BUU, which is called a quadratic form, and we call it QU. So this is similar to generating a norm from inner product definition. So based on these three definitions, we are going to prove two important results. Not prove, without proof, we are going to state two important results that are going to be of use to us. So the first result is that if A is a strictly positive operator in some domain D, and F belongs to H, which is H0 in our case, or L2, then AU equal to F, this differential equation has at most one solution in D. So that means the solution that you get for U in case A is a strictly positive operator is unique. The second theorem is that if A is a strictly positive operator, then we can generate the quadratic form u equal to half uh, au comma u minus fu. So this is the first inner product and this is the other inner product that you form with the right hand side. So minimizing this quadratic functional gives you the same result as solving this. Remember, if the solution of this is u equal to u naught, if u equal to u naught is the solution, then that's a unique solution. And in that case, this would be the functional that you have to minimize in order to get this u naught. In other words, u naught will be the function that will minimize this functional in case au is a positive operator. To prove that au is a positive operator, what do we have to do? We have to show that it's self-adjoint or symmetric, and then we have to show that it is strictly positive in the domain of interest. So we will do a few problems, but what I want to emphasize here is that if you have a equation of this sort, then you can write down the variational statement right away using this principle, using this theorem. You can write it down at once if you know that A is a strictly positive operator. We'll see some examples in the next installment.